go to homogeneous transformation. Homogeneous, hopefully I spelled correctly, homogeneous transformation. Why they call it homogeneous transformation? It's pretty much out of the scope of this course. You can look it up. There's a particular reason for that. But what we care about is that we want to just condense the rotation and transformation when we have rotation and both rotation and transformation. So we can write it simply. I'll just give you the final, I would say, procedure. Let's say rotation and transformation can be represented by a 4x4 matrix or 4x4 homogeneous transformation matrix. And we call it, we usually represented with TG transformation from local coordinate frame to global coordinate frame. If you use this matrix, 4x4 matrix, which I'm going to define what its components are, you can just easily write R in global coordinate frame is transformation matrix going from local coordinate frame to global coordinate frame multiplied by the position of the point in local coordinate frame. All right, that's all you will have. So that plus D, I'll show you that now it's incorporated into this transformation matrix. Now, this transformation matrix has the components of this transformation matrix from B to G, or from whatever is subscript, whatever coordinate system you are going from to whatever coordinate system you're going to, right? B to G, transformation of the components or coordinates from in frame B to frame G. This is a matrix in this form. This is a 4x4 matrix that has your rotation matrix, or G. We can use B here, rotation of local coordinate frame in global coordinate frame. DG 0 and 1. Now this, if you divide this in this form, this one is a 3x3 matrix. This one is a 3x1 vector, and these are just single elements. So if you want to expand this, you can think about it this way. You can think about this as a 3x3 matrix with all the components of rotation matrix you know from before. R1, 1, I'll represent that with R1, 2, R1, 3. It's just some placeholders I put there. R2, 1, R2, 2, R2, 3, R3, 1, R3, 2, R3, 3. Now, maybe I should have mentioned that. This is a 1x3, and this is a 1x1. So these are 3 zeros here. And then you have DG. So DG, you can think about that as wherever the position or D in global coordinate frame is. I'll just represent that with X naught, Y naught, Z naught, and this is just 1. So this is a 4x4 matrix. Now in this matrix, there's nothing you don't know. There's everything there you already know. You know that, let me write this way. This is your rotation matrix from before. Rotation matrix, like R, could be R about X, about Y, about Z, whatever, depends on what R you're looking at, the components change. This is your DG, which you already know from before. And 0 and 1s are just 0 and 1s. They're always, those components are always 0, and this component right here is always 1. So if you do the multiplication, you will see you get the same thing as before when we had RG is equal to RG RB plus DG. It gives you the same thing. We just took DG, put it into transformation matrix, so we don't have to have this extra plus DG here. I will see the benefits, as I said, when we have multiple transformation. That helps a lot. So just to make sure that everyone is following, this TB is transformation, or let's put it this way. It transforms the coordinates from frame B to frame G. I guess that's the best way I can probably describe it. So you want to expand this? Well, let's just leave it like that. But you can think about this as let me see if I can. I don't want to add too much things there. Adding too many details will make it more confusing. So TBG basically is a homogeneous transformation matrix, as they call it. It's a 4x4 matrix that maps a homogeneous or a position vector from one frame to another frame. In this case, it maps the position vector from frame B to frame G. So it maps whatever you have in B frame to whatever you have in whatever you will have in G frame.
Question.
Go ahead, Lucas.
So, do we still have to worry about the order of the transformations? I previously said that we work from the last transformation and work our way to the first.
So it's still going to be this. It's still going to be from the last to the first. You will still go over a couple examples, and we'll see. We still go from the last to the first when it comes to translation. So now we have. Let's say you want to go from frame B to G. This is if you have multiple frames. I'll talk about compound homogeneous transformation. It would be B1 to G, then B2 to B1, then let's say B3 to B2, and let's say we want to go from B3 to G. Right? We'll talk about it. Now the story changes a little bit. You look at the whole picture, the rotation and translation, and it'll say, well, which frame are we, and which frame we want to have the coordinates of the point in it. I'll talk about it's under compound homogeneous transformation. Right? When you have multiple transformation, and that's the whole reason that we actually moved from rotation plus translation to general matrix transformation matrix that can actually help us to deal with compound homogeneous transformation. Hopefully it makes sense to this degree, but what I can tell you is that we'll get back to this and we'll talk about this actually under compound homogeneous transformation. Right? Well, this is just the beginning, homogeneous transformation. We get comfortable with this, then we'll talk about compound homogeneous transformation and what happens when we have a series of transformations. So you can just write it here, just as the final thing I want to mention. So let's say the transformation matrix, transformation matrix T T maps a position vector from one frame to another. Right? You can say this just pretty much can put it this way. This is just to simplify the calculations. And so this is the same as what we were doing before. We just changed the representation because this is just going to help us for calculations when you're doing multiple rotations, transformations. I'll go over two straightforward examples on this in the next class. And then from there, we'll jump into homogeneous transformation and how we can actually use homogeneous transformation when we have, as Lucas mentioned, that when we have, let's say, how do we deal with multiple frames and how do we deal with, that's basically where we are going in robotics, right? We don't just have one global and one local. We're going to have one global fixed frame and then another frame attached to the first piece or link in the arm, another frame attached to the second arm or link, another frame attached to a third link. So we're going to have multiple frames. Now, this homogeneous transformation and the procedure that follows helps us to deal with that situation. But just, you know, it's not coming from thin air, right? It's just basically what you were doing before. Rotation matrix and the translation vector are just within this transformation matrix, right? I'll just stop here because those are just two examples we'll do. I'll start from this slide next class.